Thank you for having me. So, I start every year by saying it's good to be back. So it's really exciting to see that at this event, we started, say, in the first 4 years, really in technology, saying, let's build this thing, let's figure out how the technology works. And in the last 4 years, we started moving to industrial applications, to really the hard things that makes a lot of money, effectively. So today I'll be talking about exactly that. So how do we distribute precise timing with LoRaWAN in Class B? Actually, it's very, very useful, very good at this, to really unlock applications. And we'll first look at a bunch of these applications so we can see what we can do in buildings, in industrial sites, with bridges, mines, underground, and a lot more. So let's start high level. We first look at applications. So we can do structural health monitoring. The simple way to think of this is we don't want the bridge to collapse in a basic sense. So what does that mean? We want to see if it's standing upright. We want to give it an impulse. So, me jumping on the stage, you would see the waves across the stage rippling through the structure. The same happens on the bridge, except you maybe have a truck or an impact tool hammer, which gives you an impulse response of the bridge, and then it will respond to the mechanical perturbation. So we can tell if this bridge is standing, and we can see over time what happens with it. In the industrial condition monitoring, we can look at equipment like generators, we can look at power plants, we can look at any industrial process, and see how do measurements precisely correlate across a physical structure. So, for example, if you look at how long does, say, a mechanical impulse travel through a structure, or, for example, if it vibrates on this side, what is the whole structure doing, or how much vibration is going from the machine to the ground, and all the various things of that sort. And lastly, in test measurement and research, it's really hard often to measure things to validate that what you build works correctly. So for example, if you want to measure the vibration in a wheel on a car going down the motorway or a test track, you need to put sensors on a wheel which are wireless, and preferably you would put that on all the four wheels, and you really need to have a precise timestamp across all the data you collect. Or say if you're building a jet engine or a rocket or anything along those lines. So specifically diving into all of this, when you look at the bridge, for example, you will see it wobble about this way. So if at every point of the bridge you put an accelerometer, you will see that point moving up and down and left and right. Or you put a strain gauge or any other kinds of sensor. Now the speed of that waves and the vibration is often pretty fast. You will be looking at things up to a few kilohertz. So the timing between those samples needs to be very precisely aligned between all the points. And if we do a thought exercise on, saying, placing 200 sensors on a bridge and running the cables to each and every sensor, you will see that the cost of deployment is mostly running cables. It's not actually installing sensors and doing something useful. So we want to do this wirelessly. That then enables us to detect sudden failure modes. So for example, you look at how things behave every day, and when it's strange, you stop the traffic. And with that, we do long-term degradation monitoring. But for the long-term monitoring, we need to have the lab-grade quality of data collection over a long period of time on a specific device. If we go to a lot more complex installations, such as the lithography machine to make chips, or CNC machines or pick-and-place applications, in a lot of cases, we want to characterize vibrations in moving objects without having any cables in place. So for example, if you look at the heads in a pick-and-place machine or in some very fast industrial process, there are things which move with 50 meters per second with acceleration up to 50 G. If you want to measure things, you can't have cables following the motion that fast. So we want to do this wirelessly. Another interesting application is when you have a bunch of these machines installed in one factory floor, does one machine running, creating vibrations, conduct it through the building to the other machine and causes the defects on that machine? And lastly, we have problems, particularly with high-speed motion, where the machine itself will deform because of high loads and the motion. So if you have a carbon frame, it will deflect with a particular mode. And we go in further, so we go underground. For example, you have a mine or a tunnel or a cave. You want to have a large set of sensors there to see if the walls start moving, if the pillars start collapsing, or various kinds of things like that. And again, if you do that in a wireless manner, it's pretty painful. Wirelessly, you can do it with LoRaWAN pretty well. Another interesting one is what we show in the image below is the pressure distribution within a building. So a very typical LoRaWAN use case is having temperature, pressure, humidity, microclimate sensors in a room. So every 5 minutes you get these are the values. But using the same hardware, you can do a precise time sync and then measure the pressure based on the time sync. So when someone opens the window, you will see how the air pressure change propagates through the building from room to room. And if you have all of the data with where the air is coming in, how the wind is outside, you will get a pressure differential across the rooms, time synchronized. And then when you do a change, say in the HVAC system or something else, you will see how it reconfigures. And with the delays in propagation of the pressure, you can do quite some math and figure out how the building behaves. So we can do a bunch of all of these things, but we need to do it somehow. So here's how we go about doing it. First, we need to select a technology. So I have a very easy selection chart here, which is you should use GNSS, PPS, so precise time pulse synchronization, if you can. So if you have Skyview, if you have GPS, use that. It's by far the easiest and the best thing you can do. And if you don't have Skyview, you can use a bunch of other technologies. So you can use Wi-Fi, you can use Bluetooth, you can use LoRaWAN Class B, or you can use just pure LoRa, say on 2.4 gigahertz. Now, there's benefits and drawbacks of all of these technologies, generally in power and range. So for, let's say, if you're doing a solution within a short range of a few meters, Bluetooth or Wi-Fi will be your go-to solution. Because it's easy, you can send quite a lot of data, and usually you're OK with power. But as soon as you need distances of tens of meters or 100 meters, maybe up to a kilometer, really you can only do it with sub-gigahertz on LoRaWAN. You can do it maybe with LoRa 2.4 with ranging, which is really good for precise time sync. But you don't have the standard gateways and all that at that band, so 868 is still the best option. So specifically, what unlocks this application with LoRaWAN Class B? So a summary for LoRaWAN Class B is that you have an extra RX window, an extra RX slot for the device. So the device sends an uplink, you have RX1 and RX2 windows, and then sometime after that you have a configured downlink window where the network server can send a packet to the device. Now, for that window timing to be feasible, you need a time sync mechanism. So per LoRaWAN standard, you have the device time request mechanism, which gives you the UTC timestamp to the device. It's not exactly precise, but it tells you the actual time. And then when you use the Class B, there's beacons, usually every 128 seconds, and those beacons are precise in timing. So they're transmitted with 1 microsecond accuracy from the gateway, because the concentrator ICs have a GPS PPS input, which will trigger the downlink. And that means all of the devices there will receive the same timing, and you can synchronize them with that accuracy. So in practice, that means we can take our GPS reference. So for example, this is something like we would get from GPS. There's some fixed propagation delay through the gateway, through the device, but it's predictable and reliable. So from this point to 4 devices on this point, we see that they are aligned. And they're aligned in our experiment, for example, with under 600 nanoseconds. So it's pretty much perfect for time syncing all of this. And it's precise enough that we can see RF propagation delay over free space. meaning that we put the sensors along a building, we'll measure the time the RF wave takes to propagate that way. So we get about 1 microsecond every 300 meters, so this gives us about a 300 meter resolution. If you were to use the LoRa 2.4 gigahertz with the ranging, this would be a lot more precise, and you can get to some number of nanoseconds for even more precise timing, but you cannot use the whole LoRaWAN infrastructure with the gateways and all that exactly the same way. So, in practice, what does the device do? How does that work? So, on the device, the only part you need to do extra is you need to track the timing of the DIO pin from the LoRa chip. So the DIO pin will go high when the chip receives a LoRa message. So pretty much here, you are in this is the state machine of the transceiver. You have an RX done event. There will be a pulse. You will take the timing out of that. Now, because the LoRa transceiver will give you a bunch of interrupts, you need to filter it out and figure out only which one aligns with the RX done events. So that gives you your precise time when you can start sampling the values on your device. And then you need to be mindful, because LoRa devices are usually pretty bad in terms of clock stability. There will be some time drift over the next 128 seconds when you get a new beacon, so you can resync and correct the time. Some of the challenges with this is Class B takes a bit to set up, which is about 130 seconds or so in average, which is pretty okay, but some applications that might be an issue for you. You can set the beacon intervals to a non-standard value, so this can be faster depending on the spectrum and use. There's some limitations you need to keep in mind with the gateway. So if you have a lot of adjacent gateways, they need to have a different channel for the beacon. So the network server should really allocate that to the device. And you need to keep in mind, if you have large physical distances, you need to account for the propagation delay of the actual signal between the gateway and the device. But you can use whichever positioning method to figure out where the devices are relative to the gateways, and you're at the point where you know the precise time. So with all of this, you can take these applications or pretty much any other application you come up with, give it a precise time sync, and get a lot more value from the hardware you already have in place. We built a bunch of these products for industrial monitoring, for bridge monitoring, and things like this. So we're doing these kinds of projects, and would be happy to discuss with you guys. If you have questions, ideas, project concepts, you can find me at the IRNAS booth or somewhere next to the venue here. Thank you very much.